Okay, so this is the last lectures we have, and let's see what we have is content-based multimedia retrieval, and this is a very exciting topic in multimedia research, in multimedia, latest development. So, and all of the knowledge that we have and learn, so that can be linked and applied, here in content-based multimedia retrieval. So let's have some idea on it. So we will mainly have an overview. So and we will see that how to do this kind of things, the concepts of content-based image retrieval, audio retrieval, document analysis and retrieval, and overall system architecture, and some multimedia event detection and event context. So let's start with content-based image retrieval. As you know that when we study multimedia, so mostly we focus on image. Basically, image is one of the core parts in multimedia, and other text, audio, video. Definitely, those are also coming more and more prominent. But once you have this understanding on the image perspectives, all other things become easier to accumulate and to link. So, what is content-based image retrieval? So it's very simple. It is simply searching for digital images in a large image database. So that's it. I mean, when we Google, then Google we do text searching. We provide some text and query, and then lots of other relevant documents comes in. We can also search image in the Google, but the result is not that much satisfactory yet. So ultimately, the content-based image retrieval is a way of querying the image database. So that's it. And what is the search items here? The search item is basically the visual properties of the image. So that's the search item that we need. And in return, from the database, it sees that what are the shared and common characteristics or visual properties. Then that image basically comes at the return result. So that's the the main theme in content-based image retrieval. So the example is like this. Let's say we are searching something like deep blue sky, and perhaps this kind of things comes in. Now, of course, results might not be satisfied yet, but doing good jobs, and progressing day by day. Also, for example, the orange sunset might be look like these kinds of return results. And it's not only just about image. People are nowadays is basically look for the objects, in even human activities. So those are also coming, and this might the results might come in the form of image. So before content-based image retrieval, it was all about text-based image retrieval. Of course, we are using the text-based image retrieval. Is still that's the very dominant and prominent approach for searching to search engine. And text-based text-based searching is still the market share is huge. So, and that we can understand from the profits from the Google and that kind of company. But this kind of, for example, so that let's say this image, the content-based, text-based image retrieval, how does it work? So you see, so generally it was kind of that manually we provided some tag, right? For example, this image, when we look at, maybe we embed some metadata. For example, cherry trees, is bloom condition in springtime. So it's all about, but it is definitely a labor-intensive job. And often it might give you imprecise result. For example, you look for apple, maybe this apple, but these apples is also, this is semantic error that's also might have, right? So this kinds of imprecise result is very common. So there are a lot of applications of content-based image retrieval. For example, art collections. So especially in Fine Art Museum of, let's say, San Francisco, they have lots of art, and it is good that they can, if they can search those images based on some image searching mechanisms. And also, for example, these medical image databases, there are lots of images, this computer tomography, magnetic resonance imaging, ultrasound, and various others, right? So if we can have some sort of image miner, for example, this image miner software, it can basically detect that, let's say if some new disease comes in, then this new image of medical, then it basically record that which is analogous to the medical image database, and then based on this matching result, maybe they can have some idea that what kind of disease it might be, or what kind of relationship it might have with our existing knowledge. The content-based image retrieval is also used in scientific databases. For example, in art sciences, the art sciences, works with lots of, geological images, geospatial images, earth images, and in various kinds of uses we can use those kind of things. For example, environmental study and various other things. Also, we can use content-based image retrieval in general, licensing purposes. For example, we can relate these things, kind of, let's say, car licensing, car plate, right? So you have some, car plate, a car is coming, and then you have a photo, then you can actually, match this photo with your repository archives, and then it is real, real or not. This kind of things we can do by automatic process. And definitely the World Wide Web, the internet is a big, and a source of, this content-based image retrieval, right? Also, these kinds of things, for example, law enforcement agency also can use, this kind of, photo enforcement or something. So how basically it works is very simple. You see, for example, this is a simple photo, face photo. So it basically can, identify from this photo different kinds of, geometric metric. For example, what is the distance from this portion, this place to this point? What is the distance from this point to this point? And what is the angle between, right? And what is the angle here, angle here? So different kinds of, numeric metrics and features can be generated by a simple photo. And those, metrics we basically use, to search the similar kind of, photos. So what's the query that we are talking? Definitely the image that we already have, this query. In additions, if we might have some rough sketch, for example, you maybe look, okay, you don't have the photo, but you can, create a sketch of some unknown person, and then you can search that, okay, if it's possible to find that person. And also the symbolic description, whatever we want. For example, we can have logical representation of some data, and that we also, like to search. For example, this spatio-temporal logics. So what is a spatio-temporal logic? Temporal logic is relation to, some sort of time. And for examples, we may say that, I am hungry. Now, I am hungry is basically, it's in reference. This might be true or this might be false depending on the time. Sometimes I'm hungry, sometimes I'm not hungry. So depending on the time, this logic might be true and false. So that kind of things. So when the data basically, somehow has, time dimensions and as well as the space dimensions, so that, and then your logic depends on that. So, and there are many events basically, of that kind. So that kind of things we say is spatio-temporal logics. And if you, represent that kind of logic in terms of image, that also might be your query. So how generally it works, that's a content-based image retrieval systems. So you have this query image that you are trying to find out. And then from this image, you basically, find some features. So that is called feature extraction. And then you have then, query image features. And on the other hand, in the offline, you had a lot of image collections, and there are a lot of these big image collections. You basically has then feature, extraction from all of these images. Then ultimately you have a feature database. So these two stops, then you basically, online, you basically, try to find out the similarity between this and that. And then you return the retrieved images. So if we like to see, this block diagram of content-based image retrieval, with something called feedback, then it looks like that. It is the same offline processing. You have the image database, and from there you basically extract the feature. So as you have feature database, and you are providing the query as the image, and then feature query, and then you basically do the indexing and matching. So you get the retrieved result. But sometimes this is not the satisfactory. So user itself now play the role. He can modify the query, and then some feedback goes in. In this way, the result might be improved. So definitely, as you can imagine, as you can understand, the users basically play a vital role, an active role, to develop an effective content-based image retrieval system. So what is the idea of this image features? How it works? So let's say this is the user and this is our image. So, based on this image, let's say we try to find out some features. So features, you can think of this as a vector, right? From this image, maybe we just find out some, a vector of some numbers, right? And that's the your things. So this is the features. And from the image database, so that means for each image you basically have that kind of array of numbers or array of a simple data. So that's the features, because this image itself a lot of dimensions, right? Higher dimensionals, and it might have a lot of pixels by pixels. But from there we basically somehow extract a characteristic vector. So that's the characteristic vectors. So in a nutshell, it's basically an array of numbers. We can think of in this way. Maybe for this image, this is our vector. For this image, this is our feature. For this image, this is our feature, right? So we can say this is basically image feature extraction. It's ultimately collections of some vectors. And then this feature, what we do is basically we compare these features with this feature, right? And then we basically try to find out the similarity. And what is the basic mechanism to find out the similarity? You can understand maybe that it is basically we find out some sort of distance between this vector and this vector. And the one usual distance measurement is basically Euclidean distance, and you know that what we mean by Euclidean distance, right? For example, if you have a vector like I don't know, maybe A is a vector, and let's say this might have something like component A1, A2, and in this way maybe AM, I don't know, maybe AN something. We can say this is a vector, right? A vector of some numbers. And maybe other vectors you have, that is B1, B2, and up to Bn. So what is the distance between these two vectors? So definitely we can say the distance between the two vectors is maybe Euclidean distance is A1, and you just take A1 and then minus B1, right? And then you just take the square of that. And maybe you take A2 and minus B2 and you take square of that. And in this way you just take like this one, that AN, maybe AN minus BN, and you just take square of that. So this is the summation of all of these differences between all of this component, right? So this summation is basically our distance, we can say. And more appropriately, this is Euclidean distance. So we are saying that sum over all of these dimensions from I equal 1 up to n, and then you perform this kind of things. And so is basically we say L2 norm, right? So this is a very simple our middle school and high school understanding. And then we see that which one provide the minimum distance, perhaps, right? For examples, we will measure the distance between this vector and this vector, and again between this vector and this vector, and we will find that which one provided the closest distance or the smallest distance. Then that would be our retrieved images. So that how generally it works. So what are the other image features we can think of? Image features might be color, So I mean that image features that we are talking about, this kind of features or vectors. So what is those? What are those? Color itself, as you can imagine, that histograms of image might be some features, and histogram ultimately is basically a vector of some numbers. And the textures of the image. What is the texture? The texture is basically that how some pixels are closely related, right? A group of pixels, they have something, some sort of similar characteristics or pattern changing things. For example, this one, this is basically natural texture, right? And this is artificial texture. So this texture itself also might be your image feature. And then you might have shape. The shape is also image features. And in an image, if we have some object and what kind of relationship you have between that object, so that's also might be our feature. Definitely this is the most powerful, right? So for example, like this, see sometimes when we find out the features, we can basically come up with the features, object oriented features we can do. So it's even more appealing and more effective. So you have this again, this query image, and from this kind of query image, we basically have this kinds of feature. but this features is now basically, resemble some sort of object. So from these features, we somehow generate this kind of, object. So it's a very, lower dimensions compared to these images, but now it has some sort of, object, shape, right? So similarly, based on this image, perhaps, we find out this kind of, object feature, and this is basically represent this one. This is building, so maybe this kind of features is more appropriate. This is the dog feature. This is again, this is the sailing feature, this one, and this is again the boat feature, right? And then, this object-oriented feature extractions when done, we basically, do some sort of categories, between them. For examples, we can have maybe, definitely, when people search, they have some sort of, predefined categories ultimately, right? So for example, we might search animal categories or building categories, transportation categories, those kind of things. So we make basically a very extensive list of categories, subcategories, that kind of things. Now when these things come, these objects, so we can determine, okay, this is basically a boat, and which ultimately these are transportation categories, and then we find out that in transportation categories, which object is basically goes in. So maybe in transportation categories we can say there's sailing or boating, so these two basically the retrieved images. So this is how we can understand it. Then we have audio retrieval. So audio retrievals has huge applications. For example, automatic speech recognitions or speaker identifications, and music information retrieval. We like to collect some a particular class of informations or particular genre of music information. So we need this kind of classification retrieval, and sometimes we also need this kinds of environmental sound recognitions for the purpose of acoustic surveillance, right? And we also we need this kind of content-based audio retrieval for audio segmentation. And audio segmentations, we also say audio classifications, is basically generally a pre-processing steps in audio analysis, right? And that kind of a segmentation is required for different types of for example, you need to identify if this is speech or music or it's environmental sound, silence, or combinations of these things. So that's why image classification is important. So the major challenges for this content-based audio retrieval is basically that what kind of features that we need, right? So and that the audio itself might have different class. For example, so it might be music, and it might be speech, it might be other, and the speech might be male, female, or maybe some sports announcer. The music's also a lot: country music, classical music, disco, hip hop, rock, jazz, orchestra, core, piano, and string quartet. A lot of kinds of audio we might have. So it's a very lengthy process, and it requires lots of computational and resource consumed job. Okay, so then we have something that what is the general mechanisms or simply a functional block diagram for a audio retrieval systems. Again, it's similar to the content-based image retrieval. For example, we have the audio database, and then we do the feature extraction based on that. So we have the feature database, and we have some sample audio that we like to search. So from the sample audio, we have extract the features, and then we formulate the so that features goes in here. And definitely once this results comes in, we also might need to have some sort of feedback, right, to refine our query. So this is basically with feedback. So audio retrieval with feedback. So the task, for example, is simple space recognition. Simple space recognitions needs different kinds of modeling. So it involves acoustic modeling, lexicon, and language modeling. And you have some idea that what we learned before in terms of acoustic modeling, how that kind of things works when we studied audio compression and audio signals itself. So anyway, so these things are a little different because it's more about speech signal processing and recognitions. But anyway, so let's see. So this acoustic model is basically describe the sounds, right? That what makes up the speech. Not all the sounds makes speech. So there are some particular sounds, right? And then again, if we can identify that yes, it is basically speech sound, then we need to see that which sequence of speech makes the valid words. If you just say some word from your mouth or tongue using your human speech systems, and so any kinds of words, any kinds of sound that you say, it might not make the word, right? So we need to apply some lexicon model to find out that yes, this is a valid sequence of sound, and finally this sequence probably makes some words. So that kind of probabilistic modeling we need to fit. And after we have some valid word, then we need to see that what are the various sequences of the words that we can say, and then we can find out some likelihood and probabilistic calculations to find out that yes, so that kind of speech is coming. So generally, these are the process, when we have this speech and do some initial signal processings. So the acoustic modeling, basically the phonetic probability, and the lexicon modeling is providing is the pronunciation, and then we supply the grammar, then we find out the language modeling, and then finally we see that speech, we recognize the speech. And then, apart from that, we have something called document image analysis. The document image analysis means that we have an image, but that basically, is basically also contains some documents, for example, a lot of text, right? So how we process that one? Definitely, we need to apply something called OCR, optical character recognition. So we need to convert the page images to some, Unicode, characters. So that might be handwritten or might be, machine printed or whatever it is. We also need some other kinds of, pre-processing. For example, we may need to find out the page layout in the beginning, because, once you have the page layout and then that what is the margin, what is this, so you now can identify the, text and something, right? So it is not, similar to speech or simple text. It is completely different. So this is in a simple block diagram that you first identify the text area, that in the image which area is basically text, and then you do some pre-processing on the text area, and then you finally apply your optical character recognitions to find out that what are the text associated with that image. So, for example, this is the text detection, right? For example, the CNN, image frame, a video frame, and then within you basically first identify the image area, and then you basically apply the OCR here. Similarly, do for every. This is just for example. So let's say we have a multimedia multimedia documents that, or multimedia itself, that base or multimedia stream, so that has basically text, image, audio all together, and the video is basically a sequence of images, and so that's why we didn't show the video separately. So ultimately, then you find out the text, you find the image from your query, and then you find out the audio, and then you basically based on your search, you basically give some score on your text, on the text that you find, and on your image features, you basically provide some score on the image, and then you give some score on the audio. So ultimately, you have text score, image score, and audio score. You basically combine all this together, and then you basically come up with a final score. Final score means a final vector, and then you see that okay, then from your database, you basically all you have that kind of let's say a multimedia streaming or multimedia clip or whatever. So you basically do you take this kind of this one, and you perform this kind of text, image, and audio, and you give the scores on that, and you find that which scores basically become similar. So that's your ultimate result. So apart from that, another big things in multimedia content based retrieval is multimedia event detection, right? For example, let's say this is basically we are preparing and making some shelter, right? So, and you see this is a shelter preparation. This is also shelter assembly. This is also shelter assembly. This is also shelter assembly. But it seems that all the scenes and people are mostly consistent. There are people and scenarios also like this kind of scattered and little bit that those are consistent. But the shelter object is basically vary. The shelter object is like here is like this. Maybe it's some kind of tent, but here is completely different. here is also different. So we need to find out that kind of consistent, and what are the variation. So and then based on that we need to find that what is the event there. So another example, more for example, this batting and running. Think about a baseball or maybe something, or maybe cricket or soccer. So anyway, so you see the scenes are basically consistent, but it seems like one environment might be mixed up with other. For example, you can equally interpret this thing as a cricket, or maybe you can think of it as basically baseball, or sometimes even confused with the soccer environment. So that's the idea. Now, how about here? This is basically, is basically even different kinds of things. Here, main idea is the activity based, right? For example, you are preparing a cake, so you need to identify what are the actions and activity going on. So then you basically comes up. It's basically mixing, right, of many things. So we really need some sort of discriminative semantic basis for this kind of composite event modeling. Now here is one particular context. Let's say how to understand that. So let's say the condition is batting a run in, so baseball run when the players take some run. So it has some scene concepts, might be sky, you see. Then there might be what are the grass, and this might have the baseball field. So we need to analyze this kind of concept. We say scene concepts, and we can also might need to analyze the action concepts. For example, they are walking or they're running, and also we can we may need audio analysis, audio investigations, that they are cheering or clapping or simply speech. So based on all of these things together, then we can understand the event context, right? So understanding context in multimedia event detection is very vital. So now, having said all of these things in our courses, definitely there are a lot of research topics still open. So we have this in the age of this big data and AI, we have huge opportunity to work on multimedia information retrieval, right? You can work on deep multimedia networks, large semantic networks. There's a lot of knowledge graph and networks. You can identify the social networks, behaviors, people, right? So those kind of things. And as we studied before, that's AR, VR, and CV, that is computer vision, is a big part that we can relate to multimedia. And then as we studied the first part, that synthetic media, that is that we studied the GAN, that generates adversarial networks. So that generate basically the synthetic images. So this synthetic media is a huge thing. That means artificially generated media, artificially generated image, artificially generated video, artificially generated many other things. So these are very challenging. So we also say this basically deep fake. So as you can imagine, there are a lot of many exciting research problems, and perhaps you might be interested to invest some of your time, and you can choose in this area, right? So so this is it, and finally we come at some places that where we have finished our courses. And I believe that you guys that who basically really studied my courses this time in multimedia, you basically learned a lot of things, and it's amazing landscape, and I try to cover a lot. And this time I covered 50% new content, almost more than 50% new content here in these courses I gave you. In the previous times, in previous semesters, I didn't cover this much, but I did these times. So before midterm exam, we basically covered very a very detailed understanding of what we need to have the basic framework for multimedia understanding. So we started our multimedia data, and especially the image fundamentals, right? Image fundamentals. Then we started color science. Color science is very important, and color models, in fact, right? Different kinds of color models, and color models are very important. you can still refine your understanding on color models. It will be helpful. Then we saw that what are the basic mechanisms for image compression, because image compression is really important, that especially in this today's world where a lot of images are being produced, and maybe your service provider need to have some sophisticated mechanism to compress the images. And then we studied that how audio compression works, especially simple audio and audio compression. Then we studied fundamental concepts of video and video compression. So, and then we also see some basic multimedia tools, for example FFmpeg and some others multimedia tool, but FFmpeg from programming point of view. Then after midterm exam, we then started with maybe data visualizations. And the data visualizations, even though it's not exactly multimedia, but it's highly related to multimedia, and I thought it is good that you also know some design perspective from visualization perspective, and you can combine the multimedia concept and design concepts with the data presentations. So that's why it is very important. We saw some principles of animations, right? Because this is again is highly related. So its main branch is coming from graphics, computer graphics. But when it comes with our multimedia, we need to have some basic understanding how animations usually works, so especially from the design perspectives. Then we also studied AR VR, and I believe that this understanding of AR VR, data visualizations, and principles of animation together, it will motivate you for further studies in these fields. Then we saw a very promising and very useful technical GAN, that is generative adversarial networks, and this is nowadays superseding all of the many of these existing machine learnings, or we can say neural networks approach, that how deep fake media works. So if you understand this, if you can apply these things to your research and your works, it will be so useful. Then we also understand the multimedia communication networks, and we saw that which protocols are basically better for our multimedia communications. And then today we saw some concepts on content-based multimedia retrieval, right? So altogether, I believe that we got an array of and concepts, and this constitute the landscape of multimedia. So you learn from both design perspective, science and intuitive perspective, from engineering context, and as well as application perspectives. So you got the whole landscape of multimedia computing. So I wish you good luck for the exam. So you give the exam and submit the your project, and we will also have another I have already given you one assignment. You also do that, submit that assignment, and then it will be good. So I believe that you enjoyed the course, even though we didn't meet in person, but I believe that you have some good feelings throughout this course and our interactions by emailing and by texting, by other kinds of forms, and then mostly you got my voice. I believe that it will be a very pleasant memory for you and me. So good luck for you, and see you next time.